All righty, let's go ahead and get started. Good afternoon and welcome to today's webinar, Digital Integration of the Stamping and Body and White Process Chains, which is one of the keys to mastering the challenges faced by car body engineers today. Those challenges are due to trends like electrification, new mobility concepts, autonomous driving, and shortening the time to market. The webinar today is presented by Autoform Engineering and hosted by Metal Forming Magazine at the Precision Metal Forming Association. I'm Brad Kuvan, Editorial Director of Metal Forming Magazine, and I'm pleased to serve as your moderator for today's session. So the webinar today is the second in a three-part series that we're presenting in partnership with Autoform. Before we get started, just a few notes about today's Zoom session. The meeting is being recorded for archiving. The recorded event will be posted to our website within the next day or two. We'll let you know via email when that recorded webinar is available for viewing online. Also, all of the participants in the meeting are in listen-only mode, so the speaker and other listeners will not be able to hear audio from your site during the program. But you can communicate with us throughout the session by submitting any questions and comments using that Q&A button located at the bottom of the Zoom screen. And you'll also use that same Q&A button to ask questions of our speaker at the end of his presentation. So we'll go ahead and begin the webinar. The presenter is Todd McClanahan. Todd is a Senior Application Engineer with Autoform Engineering. He's going to introduce for us an integrated methodology to simulate the body and white assembly process and predict resulting assembly characteristics, physical and geometric aspects. So please welcome Todd McClanahan. Todd.
Thanks, Brad. Appreciate the introduction, and thank you for everyone joining in today and giving me some time from your lives. I appreciate it. As stated, we're going to talk about the integration of stamping and body and white process chains. And I'll briefly show an agenda of what is planned. Basically, will be an introduction into assembly. So you'll hear me talk about assembly more, but we know that without stamping, there is no assembly, and how important these two are and how they operate together. So we'll go through some background briefly. I'll talk about some key countermeasure options to deal with issues you may have with assembly accuracy. But I'm going to focus on two key elements. The first being assembly optimization, mainly in shimming and teaching, with a short demo to support that story. And then also part compensation and a short demo again to support and show how we can work through that quickly and easily. Then I'll finish up with a brief summary and conclusion and allow time for questions at the end, hopefully roughly take about 30 minutes of your time. So if we think about what we do at Autoform, we've been known for many years on the forming side for sheet metal forming and stamping. I come from a stamping background in an OEM, and I've been at Autoform now for 8 years, but that was my previous life. So a lot of the things I worked on, I actually did in Autoform. But the focus is, of course, on parts and creating parts that are within tolerance, a given tolerance of nominal. What we found and what I often experienced myself is that once you've created tools to make these parts and you have what you believe to be good results according to the goals you had set, there are still problems when you get to assembly. And oftentimes, those assembly problems start to outweigh or affect the efforts that you put into development of the single parts, which means you have to go back and work on trying to countermeasure to fix those issues. That's why, and that was motivation behind Autoform developing our assembly solution. What that does is allow us to consider the linkages between the single parts and how it affects the overall assembly and get a better balance when we consider all of these factors. Now, I'll talk briefly about different types, I guess, of assembly simulation. The first thing I'll talk about briefly is process simulation. And there are solutions out there that really focus on the assembly process itself. So it's really getting into the simulation of the joining or the welding process. It might be looking at nugget size, other elements of the weld itself to make sure it's feasible. So that's one area that you may be familiar with in assembly simulation. Another might be tolerance analysis. So taking nominal parts, defining some tolerances for these parts, and then looking at the stack up, maybe get a histogram of maybe worst case scenarios and what your probability of having success is with those parts as those tolerances are defined. Another area that is something you can look at is offline programming, which comes into programming of robots, digital manufacturing. So actually programming the welding, the joining, the sequencing, doing collision checks, making sure you have accessibility to areas to reach to get your connections made, and also checking your cycle time or your speed. And all these are beneficial areas to study. It's not really, though, what our focus is with our solution. Because it doesn't really address always the assembly problems that we see as we start to put together the single parts. So our solution really starts to look at full simulation of the assembly processes and seeing what happens when you take parts that are not nominal and begin putting them together and predicting the dimensional results that you will find. I'll break it down kind of into existing capabilities for forming areas. First being the parts, we can bring in geometry, CAD-based geometry. We can look at making modifications. We can deal with, if you're doing hemming, unfolding of hem flanges. We can define material and thickness properties, et cetera. And really the key thing that's important to understand is we can work with base CAD geometry, nominal geometry. We can take results from forming simulations and make use of those results with stresses and strains, Springback, all of that incorporated into it. We can make productive use of scan data in your studies. So if you have parts on the floor, you can get good scans. We can make use of that as part of the assembly simulation to predict issues. And we can also map results of forming simulations to those data sets if necessary. On the plan side, basically the assembly plan, it's a matter of defining the type of assembly operations you want to have, the sequence of those things. So looking at assembly operations that include welding, other joining operations, hemming operations. We can look at curing, including thermal effects of curing, and of course, measurement operations, developing your fixturing to locate your parts and understand the accuracy. On the process side, a number of things we can start to do there, including the part insertion order, kinematics, getting the parts located and fixed properly. We can look at the join location and sequence. We can manage our hem tools. But this is where one key area is that I'll talk about today, which is our shimming and teaching optimization. And this can be used very early when you're doing feasibility studies and can even be done when you're talking about either tryout support or you're in production and supporting production as well. It really begins to eliminate, and I'll show how in a demonstration, the trial and error process often associated with shimming and teaching. And then lastly, evaluation. That's really how we start to understand how all these things come together, looking at dimensional accuracy, any formability impacts, tool forces, gaps between parts, surface quality issues, things like that. So it allows us to really evaluate that dimensional accuracy, determine cause of problems, and figure out solutions by going back to earlier areas. And I'll review that here soon. When I talk about the process chain, kind of what I'm talking about here is if you think about from early concept development of the vehicle all the way through into body and white assembly into production, there are different tasks that we need to basically work through, kind of in general terms. The ones that are seen here in red are forming tasks, which include early manufacturability studies, gets into process feasibility, process validation, tool tryout, and on into production. And then at the same time, happening concurrently, we have assembly tasks that are also feasibility studies, looking at potential part compensation, basically doing assembly process validation, and then also same as stamping side, supporting tryouts as well as production. The key is that the linkage exists now with these solutions. All these things are being done between the parts and the assembly. So if we look at the two solutions, whether you're on the stamping side at the top or you're down in the body and white side, and if you're doing simulations in either area, you're really trying to develop a digital process twin. And that's the important aspect of simulation, is that you're trying to basically simulate what you're going to build, and you're going to then build what you have simulated. On the forming side, we're doing early stamping engineering studies, getting into tool manufacturing, and then into your tryout and production. And it's very much the same on the assembly side. We're doing assembly engineering, going through our equipment manufacturing and process definition, and then we'll get into our assembly events and body and white production. Now, what's similar with both of these is that the engineering aspect of this all takes place in the virtual world by simulation. It's where the cost is much lower if changes need to be made and studies can be done. And then, of course, once we manufacture the tools, we're into the physical world, and that's an entirely different space to operate in. What's important is no matter where we are, we're doing interaction between our digital twin and our feedback to what is actually happening in reality. So the idea behind this is that we're going to be able to eliminate a lot of these physical iterations that we have to do to work out problems on the back end in the physical world by doing more studies up front in the virtual world. If we think about what's happening in most places now, there's not a lot of simulation being done for build accuracy. That means that when you get into your tool manufacturing, your process definition, you haven't really considered the impacts of having parts that are not nominal. And therefore, when you get into your build events, they begin to reveal themselves. These problems take place, and you go through a lot of these adjustments and trial and error studies just to try and improve the overall condition. The idea now is that we begin these simulation studies up front in the virtual world. So as you have your different drawing releases all the way through to your release for manufacturing, you'll be doing these simulation studies, getting this feedback. So you're now incorporating those studies, what you've learned, into your tooling and equipment. So therefore, when you get into your production or your pre-production build events, you are experiencing less pain and even able to eliminate events and get to where you need to be more quickly. Of course, when you're doing that, you're going to be able to also save yourself considerable time, money, and you're going to see improved quality on the back end as well. The thing that's great about these early studies is that when you're looking in the virtual world, I talked about these areas, the parts, the plan. Also, we have hemming, which I didn't talk much about yet. The process and evaluation. What's great is you can, after evaluating, actually go back and do virtual correction of the root cause of the problem. And that's really what we're trying to achieve rather than having to deal with the firefighting that happens in the physical space. So let's talk about quickly kind of what our goals are here. So if we have a goal to achieve assembly within a defined tolerance, do a little bit of analysis and determine where we want to implement a strategy to achieve this goal. So if you think about it and ask yourself a question, pause for a minute. You want to first understand what can be solved in the body shop. So in the assembly area itself, can I resolve any dimensional accuracy problems there? Or does this need to be solved in the tool shop? Do I need to look at the stamping tooling and make changes that allow us to have success once we assemble things together? Then it comes down to implementation. You have to decide which strategy, based on your existing boundary conditions, could be where you are in a project, among other things, would you then consider to determine your direction. If you're in the body and white side, if you're in the body shop, things are available to you are optimization and validation. So you're doing your shimming and your teaching of your clamps and your joins. You might change your joining sequence. You might change some clamping sequencing. Those are all things that can be controlled internally in the body shop. On the tooling side, for stamping side, it begins to look at correction of problems, which might include changing parts, modifying part geometry. It also might be compensation. And I'll mention VAR, virtual assembly reference, is basically making use of developing a compensation of a part that gives an overall result that is good to the assembly. But again, the idea here is of these key areas in the body shop, I would like to go back to the process if I'm dealing with shimming and teaching or sequencing. And on the stamping side, I'm going to probably go back to the parts, the tooling that makes the parts specifically. So let's look at a quick problem. We'll say that the assembly, very simply put, is not in tolerance or achieving the targets that were set for it. First thing you can look at is part compensation. Part compensation means that you're basically going to take the owner of the tooling, which is on the stamping side. They're going to have to be involved, of course, in this, but also it's going to require interaction with the assembly side, and there has to be some direction set for how much to compensate, what the specification is going to be to change the tooling. So it's a very involved process with a larger group of people. Now, another way you can look at improving an assembly accuracy problem is assembly process modification. Now, the owner on this side is the assembly equipment department, which is going to be your body and white assembly area. So they're the owner of this. The great thing about this is they may not need to have the involvement from the stamping side. They can control all of this on their own. Now, if we're talking about being in the virtual world still, if everything we're doing is just by simulation and we learn these problems are going to exist, then really either option is okay for us to decide how we want to move forward. We can look at process modification first, look at part compensation, as well as an option to improve the issues. But at some point, we actually start building stamping tooling and we start building our assembly equipment. And we've crossed over into the physical world. The comparison between these two approaches, whether it's part compensation or assembly process modification, is that part compensation tends to be much more expensive. You have to go back and start modifying a number of dies. It has to go across the machines. It has to have gone through the welding process in advance of that. It has to go back into the press. All these things have to be tried out. There's a much longer timeline to do that versus just looking at assembly process modification. So timing is important. So if you're in the physical world, if you're in production or you're doing tryouts, the best or most typical way to approach this problem solution is through assembly process modification. That's where we have a solution that allows us to try and do this a little more quickly. What we have with one of our solutions, or as part of this solution, is the ability to come in, define what clamps we want to allow to be shimmed. And by doing this, let the software actually tell us the correct position or where to place these clamps, that doing no changes to the parts themselves will actually improve a problem we may have, which allows us to have quick problem resolution within the body shop. There's actually a second benefit to what this solution does, where if we have robustness studies of single part forming simulations, we can actually look at those in assembly and we can identify which parts have the most influence on dimensional accuracy in a given area. And that's kind of really important to understand for a number of reasons. One, it might impact tolerance decisions, and it can also impact, if we decide to go down the compensation route later on, we can understand maybe a compensation strategy to make sure we're compensating the right parts in that scenario. So let me get into an optimization demo. And what this is basically going to be is kind of to illustrate the power of this optimization I'm talking about. So this is basically a 4-part subassembly, very basic, works well for demo purposes. But what we have started off with in our early feasibility study are 4 nominal parts. And you can imagine if you have a good assembly process and you have 4 perfectly nominal parts, then you can expect that upon assembly nodes, you're probably going to have a pretty good assembly result as well. And that's the case that we see here. We can see that we're comparing a range of plus or minus 1 millimeter as a tolerance. Everything is basically in the green area. And immediately you don't think that you have any problems. But that's not the reality of what we see. What we see are parts that have stresses and strains in Springback. And so what we've done is we've taken and replaced all those nominal parts with 4 different parts. Part 1 is actually a simulated result from our forming solution that has Springback associated with it. The other 3 parts in the simulation are all based on scanned results. So they are all parts that were scanned that have some amount of twist to them. They may be in tolerance, but they are, of course, not perfectly nominal. So the idea here is we want to understand, as we look at this, and we are looking again at our same plus or minus 1 millimeter tolerance, we can see on that right end down here, the area, the top side of that end is blue, showing that we're high on the minus side, and kind of compare it going back to the nominal. The lower side down there in the bottom area is red. So we have really a twist that has happened here, and usually these parts being more of a thicker or high strength steel, it's going to create some issues for us when we start to maybe join that to our body side outer. So we want to see if we can't, through optimization techniques, improve the accuracy result of this part or of this assembly. So what we can do is go back to that assembly, and we're going to go to the fixation area. Fixation is basically like how we position the parts with our clamps, with our pilots, to make sure everything is locating appropriately. But also on that page, we have an area that is called shimming. And we can add overbending to this. And what we basically do is pick a clamp that we want to allow to move, to basically be shimmed. Now, on the floor, if we're doing this in reality, we might just start applying shims and guessing. What we're going to do here is say we're going to give it a range of plus or minus 4 millimeters, a total of 8 millimeters, and allow that clamp to float in that range during the calculation. And we can do that for more than one clamp. We can do it for as many clamps in honesty that we choose to. So we'll take another clamp, give it that same plus or minus 4 millimeters of range, and we'll add a third one just to go ahead and show that, I mean, there's really no limit as to what you can do. Just understand that the more clamps you add, of course, the more iterations it has to run to study it. And I'll talk about that here momentarily. But with each of these, we've come in, we've placed those clamps. What's also important is that in this case, these are all spot welds. They've been allowed to be taut. In other words, as those clamps change positions, it's going to move the respective sheet, and the joins that are going to hit that sheet are going to travel to the nominal position where the sheet is located to also join that. So if we get these all set up, and if I'll first go and just kind of show you, in this case, there are 5 clamps that we're allowing to move plus or minus 4 millimeters. And what it shows you is it's going to study 80 realizations. So basically it's going to run a simulation 80 times with different combinations and movements to cover this range of what's happening and help us get a good idea of the path forward. So just so you know, this simulation, which has actually a lot of spot welds in it, to run these 80 realizations, this whole simulation takes maybe 2 hours. It's a fairly quick process. But once that's complete, it leaves it, when you first open it, as the nominal position. So it's going to look just like the other simulation. When I put it to the plus or minus 1 millimeter, we'll see that same twist that's taking place on that end. But we're going to go to the resolve page and apply this. And at this point, the software is going to do some study. It's going to look at these 80 realizations that have been created and begin to study that data, begin to look at positions to see if we can resolve the issues. You'll see that in the screen, there's a couple of little red lightning bolts showing areas that are known to be out of tolerance, but we also have, again, that twist that is taking place as well. So it's going to go ahead and calculate that and help us understand, again, if this solution might work for us. So we've done that first resolve. It's highlighting the issues for us. And now we have to do one more resolve over on the left, which is basically going to let the software place things in the correct position. So with this resolve, you'll see that all these sliders are now moving on those sliding bars. Our twist has disappeared. And what we actually find is that the area inside the door is actually slightly plus now. I think we're about 0.26 millimeters there, about almost 0.3 millimeters on the outside. So our twist is basically gone. We can see in the sliders, those green bars are areas that if we move those sliders within that green bar, we should have a result that remedies the problem areas. You also see here the values that are recommended to shim. It's to the hundredths position. So if you have a shim pack that has round numbers and you want to do these at either tenths, or in this case, I can do a 0.5 millimeter. But you can see that with 0.5 millimeter shim adjustments on these 5 clamps, we can get to a resolution of the assembly with some room to roam a little bit even as well. So again, this is something that if you're doing this on the shop floor, real time with physical equipment, it's a guessing game. It's trial and error. Having this type of a study allows you to go out to the floor and have a strategy, have a plan, and resolve things quickly without having to do the guessing. It also lets you think of combinations you may not have thought of just on your own if you're trying to do this in a manual situation. So that's a demo that illustrates that. So again, that's assembly process modification. Now there are situations, and hemming is probably a good example of that, where the process itself may not give you, by changing it, the results that you need. Hemming introduces basically another forming mode with the hem process. So maybe assembly process modification isn't really an option for you. And part compensation becomes what's important. As I've said though before, when you do this part compensation in the physical world with your actual tools already manufactured, it can become a very costly and time-consuming process. But by doing it by simulation, we can bring that cost down considerably, and we're not having to modify tools multiple times. So if we look at what this looks like, the stamping approach currently, this is what I used to do back when I was doing this, is you're trying to make all of your parts within the given tolerance range. And so we look at this scenario, We have 4 components that make up this hood assembly. Each of them are within tolerance, and the people who have designed and manufactured the tools have achieved what they need to achieve. The issue is, and of course we know that the goal for the assembly is to hit the target. We want to have within tolerance, a perfect assembly. With the first time we put it into the press and we hem these together, once we have the sub-assembly, we see it's dimensionally not accurate. We have areas in the corners that have gone plus, we have the window side that's gone minus. So it's all just kind of twisted and turned, and it's to be expected because you're introducing another forming situation. Now, the typical approach to this, oftentimes the inner part is the most strong of these parts, and so we will start compensating that in order to improve the assembly. The question is, what does that part need to look like? What is that new part target? And that's the challenge, because it's basically an exercise, again, in trial and error, which when you're in the physical space becomes a very costly and time-consuming situation. The idea here, if we keep this type of a study in the virtual world, is that we first achieve our target of nominal. We find out that our assembly simulation shows that it's going to be a problem. What we can do is actually go into the interface. We can spin off another simulation, calling it for Springback compensation. We can select the part we want to compensate and actually let the software determine what that new part should look like in order to yield a good assembly result. So the point of this, and this is what happens when we modify dies physically, is we make parts that are sometimes out of spec, they're out of tolerance, but they achieve a good result. And that's basically what we're saying we can do up front and save us all of that back end pain that we often suffer. But the idea is that by hitting the part target for the inner, combined with the other 3 parts, we can actually achieve an assembly that is good. So while we achieve our assembly target, we're also achieving the new part target. Again, we'll call it perfectly imperfect part, non-nominal. But we're also saving considerable time and money in doing this. So basically the idea, and I was kind of mentioning in our solution, forming allows us on the sheet metal side and our stamping tooling side to apply different types of compensation. The first type of compensation it can do is it can simply say the part sprung back this much. We'll just basically take that vector field we build, flip it, reverse it, and compensate the tools accordingly to give us a good result on the part. But the second type of compensation that we can do is we can actually compare parts and tools and also parts and parts. So in the case where we make this new target geometry, we can actually build a relationship between that, do a compensation that we can then apply to our stamping tools, so that we're now going to produce with our stamping tools this target geometry. Again, we call it VAR geometry, or virtual assembly reference geometry. And that's the idea behind this. So the idea is you have your target geometry. Once you get that out of assembly, we can import that into our forming software, set that as our target for measurement. So basically when we put things into the fixture, we're no longer fixturing to hit nominal, we're fixturing to hit the target geometry. We can generate a vector field to compensate the tooling, decide which tools we want to compensate, apply that virtually, and then we can simulate that compensated result and verify that the part indeed matches what we want it to be to give us good assembly. So basically what you're working through is you're going from forming over to assembly, getting through your first assembly studies, doing compensation of tooling as needed in forming, and then you can take that back into assembly to validate that at the end. So I'll do a quick compensation demo. I'm going to use that same part that we had in the last demo, which is a simple 4-part assembly. And the idea I'll try and communicate here is, we dealt with that twist that we saw on the right end, basically by shimming and teaching before. Now we're going to decide to compensate a part and see what that impact can be. So we see we have this twist that's taking place. It's all basically happening within that one part. Now, of course, it could be influenced by being joined to one of the other parts in the assembly. But the idea here is that we can simply, to deal with this, we'll come up and we can spin off a new simulation. Just a moment here. And when we spin this off, it's basically going to be all things are the same. We've not changed the process at all. We'll see with the 4 parts, we can decide If we want to compensate one of these, all of them, but ideally a few as possible. So we'll pick that one part, that part 2 on the end. And then what you'll see at the bottom is a compensation factor. A 1.0 basically means it's going to try to compensate 1-to-1 with what it sees from the previous result. If you want to try to overcompensate, you can increase that factor. You can go to a factor of 2 and double that if you want to, and we'll just kind of show what that looks like. Also, you'll see a slider. So it's basically smoothing. So do you want this to be as smooth geometry as possible, or do you want to lean towards the more accurate side? So you can kind of slide that and play with that as well. Now, the thing is when we apply this, it's going to go through, do some calculations based on the vector field that it has created, and it's going to morph or compensate that single part. And then you would simply rerun that simulation. I'll just kind of show you what this looks like. This is our nominal part. The input deformable, which is the mesh created for the new part, you can see is different. And if we come in and we set our a little measurement to actually understand the difference, or sorry, the distance between these two, we'll be able to see that these are indeed different. And again, I used a compensation factor of 2, so a little bit more than what the problem showed when we measured the nominal result. But you can basically see what it's going to do to this part as compared to the nominal part in an effort to correct this problem in the assembly. So that's about that's the numbers that you're seeing for compensation applied to that part. Once you have an understanding of that, you would, of course, run that simulation and get the new result. Now, I will say that in many cases, this actually resolves problems on the first try, but sometimes it takes 3 or 4 iterations of adjusting those sliders to really get where you need to be. You can see that I went through a few iterations here to do this. But when we look and compare using that same plus or minus 1 millimeter range, we can see that we now have basically eliminated that twist that we saw on the end by compensating the one part. And if we compare that to the nominal result, we can see very clearly the improvement that we achieved with this. So again, it depends whether you want to go after compensation, whether you want to wait and deal with it with shimming and teaching. But this is, again, an option to kind of show capabilities that we can simulate in the virtual space to save us that pain on the back end. Also, we'll point out that when you have that new part, so this is the part before we assembled it that we compensated, we can export that in a mesh format, take that into our forming solution, use that then to compensate our stamping tools to move forward. Okay, so that's the basic demo for that. So to wrap things up, I guess, a little bit and talk about capabilities. You can really use this simulation study. As I said, the virtual space is where your biggest benefit is going to take place. So when you're doing feasibility studies, you just receive part geometries and you want to begin to design the initial assembly process, check your part layout, identify influential parts in the assembly, and consider maybe any part changes that you need. That's a good time to be doing that. And you get to the engineering phase. You can begin to study Springback impact from reforming results. You can modify the assembly process, identify compensation needs if you want to go down that path, and also set initial tryout parameters from your first builds. On the support side, we want to resolve potential production issues. We want to reduce and eliminate trial and error that often takes place there. We want to reduce pre-production build effort and optimize parameters that we will use as we move forward into production. And then lastly, as we get into production, we want to always be able to, obviously things always change in production. You've gotten different parts off of different coils, different tool wear, all the things that take place that cause variation in the manufacturing process. We want to be able to deal with those. So we want to be able to correct part fit issues, apply process modifications, consider scans of actual parts if we need to, and really try to reduce and eliminate downtime in production. It is important to know that you get benefit from all of these areas of study, but it's definitely a cumulative effect. So as you use more of these studies and do these things throughout the entire process chain, that's where you begin to maximize your benefit by working through all of those. You'll have really quicker, more robust design process, reduction in engineering work, faster time to production with elimination of trial and error loops, and ultimately higher product quality on the back end as well. So that was the key message I wanted to share today. And I can leave a little time if anyone has any questions.
Thank you very much, Todd. Really fascinating presentation. The software is incredible. We have plenty of time for questions from our attendees. So use that Q&A panel on the bottom of your Zoom screen to ask Todd some questions. So Todd, when you're simulating an assembly, is there a limit to the number of parts that you can include in your assembly?
There's really not that we've seen. Now, how you organize it can become very important. And I tend to recommend to users to build things almost as you would in production. So focus on your sub-assemblies, and then you can actually make a new simulation where you're pulling sub-assemblies that have been made and begin to build that just like you would the vehicle in the real physical space. So yeah, there's a lot of opportunity there to really expand as far as you want.
Okay, good, thanks. So if you can't obtain a simulation for every part in the assembly, can you still, evaluate the impact of Springback without all that data for every part?
You can, and we actually have a way to do that when you're doing early feasibility studies, because as I said, and I like to start my feasibility studies with perfectly nominal data, but I start to look at, and we have something called estimated deformation. It's not doing a full simulation to predict the Springback based on stresses and strains, but it's looking at the part geometry, so the physical shape. It's looking at the material being used and the thickness of the part, and it's beginning to start to predict how it might behave if it were to spring, and that's really the important thing. So you can there's basically a slider to adjust that. You can basically say, I want to get this part. If it's a part that has a tolerance of plus or minus 1, I can slide that so I can basically get a part that when it is sprung is within that range. But you'll start to see that even with parts that are in tolerance but not nominal, the assembly doesn't always fall within tolerance. That's what's important to see.
Gotcha. Okay, good. Thanks. What can you share with us about the companies that are out there using the methods that you showed us today? How they're using what you showed us, and maybe some of the benefits that they're realizing?
Yeah, we've seen, of course, we're based in Europe, and a lot of companies started taking or making use of it earlier on as we first rolled it out. But we've now seen companies using this compensation approach with HIM closures, OEMs that have basically eliminated from their admission, not what they told us, 6 months from their manufacturing schedule for their stamping tooling as well as the assembly equipment and hemming tools. So it's we've seen a lot of that. There's actually on our blog some stories also about benefits from the optimization, the shimming optimization, shimming and teaching. It was a pretty complex assembly battery casing that they had a lot of issues with. They couldn't really compensate it because it was just so apt to twist inconsistently. And the shimming and teaching really helped them. So yeah, we're seeing a lot of benefit and a lot of elimination of some pains, put it that way.
Excellent. I was interested in your description of the use of perfectly imperfect parts. Is that reality that you see in many cases?
Yeah, and it's honestly from where I came from. I was at, like I said, Honda for almost 20 years, and so we often had to take, especially in hemmings, where we're taking the inner part or a part out of tolerance. We're having to basically, work with our end customers to make sure that they are okay with that. There's BIOS required, but really what I was saying is we're doing that type of thing anyway. Why not move that forward if we're going to do it and just get acceptance on that concept early? Because if we can prove that by doing this, we can achieve a better assembly result, then I think that's the direction to go to save that.
Sure. Good. And then at the end there, you talked a little bit about moving the data back and forth to the forming simulation software. Can you talk a little bit about how that integration works? Is that an automated process? Is there some manual intervention required there?
Yeah. So basically, if anything you want to use from our forming solution, we have a file type that we generate. It's an ASM file extension. So it's basically a file type that can be read by either interface that you're in. So if you're on the forming side, you run your forming simulation, that ASM file you can generate from there plugs dramatically in as though it's a geometry into our assembly solution. And then that same ASM file can go back into our forming solution. So it's just it's import just like you'd import CAD geometry or anything else. You're just making use of existing data.
Yeah. Gotcha. Very good. All right, I don't see any more open questions for Todd. So I guess at this point, we'll thank you, Todd, for an outstanding, really interesting presentation. The evolution of this software just continues to amaze me what it's able to do.
Yeah, thanks for having me. I really appreciate it.
Yep, you bet. So, and to our audience, of course, thank you for attending the program. We hope everyone found it to be valuable. And again, as I said early on, an archive of the program will be available on our website within the next day or two. We'll email you with a link so that you can share it with some others in your company, or if you'd like to watch it again. So again, this is part 2 of our 3-part series with AutoForm. Watch your email inbox for an invitation from us in the coming weeks for the next webinar in the series. So again, thank you, Todd. Thanks to our attendees, and go ahead and close your browser now. Have a great afternoon.